So I'm a brain scientist and AI person in the same time. So I am the one who is probably, you know, the right person to point out that there are differences, that these are not the same things. And very often you would see some companies, for example, advertising our AI works like human brain. That's not true. You don't need to read any further. That's not true. There's such big differences between how our brain works and how our technology for AI works. It's just huge. And I will explain to you a few today, so that you hopefully walk out convinced for the rest of your lives that these are just two considerably different things, right? But to begin with this topic, let us consider this guy, right? That's kind of a prototypical robot that we were promised by science fiction to have at home by now. And it would be nice to have one at home to take care of households, so we have more time to watch Netflix or whatever. But we don't have one yet, don't we? What we get instead is this guy here. And this guy is good, but it doesn't do lots of things that need to be done, because our households have a lot of other things in work to be done, right? So what are these robotic companies doing? Why are they not building humanoid-like robots to take care of our households? And to point this out, let's check one robotic company that in particular has developed a robot that can do backflips. Now, why backflips? Why would you need a robot that does backflips? Do you think they came up, like the marketing research got messed up and they figured out like, oh, the market needs robots that do backflips. Everybody's gonna be buying the robots with backflips. Probably not. But what happens is basically, that's all they could do. Well, on the right side, we need robots that can do dishes. What we get at best is robots that do backflips. Now, why is that? So there's something in AI theory that's called Moravec's paradox. And this paradox tells us that things that are easy for AI are hard for humans, and things that are easy for humans are hard for AI. And the fundamental reason is that biological brains and machines work differently. So I welcome now to the 7 differences. So the difference number 1 is type of errors we make. You can see who is machine and who is AI. You don't need to ask them questions about knowledge and how they solve problems. Just look the type of errors they make. And to illustrate that, here's a task for you. Watch this second hand and detect the moment when it skips 1 second. So my point here is that we humans are easy to distract. We could do one thing at a time, and when something else comes up, we lose focus from one side and we move to the other side. This is called vigilance error, and we humans do vigilance errors. And many of the traffic accidents that happen are due to vigilance errors. Like majority are due to vigilance errors. And machines don't do vigilance errors. If we build a machine to monitor one thing, it will forever keep monitoring this one thing. It will not get distracted. So that's one difference. What kind of errors do machines do? They do something that we could describe as stupidity errors. And this was illustrated also by Charlie Chaplin in his now 100 years old movie called Modern Times, where they built this machine for feeding factory workers. At the beginning, everything worked fine. And it even the machine could even help, clean the mouth of a person. But then after a while, things got really problematic and didn't work anymore well. And basically in machines, when something doesn't work right, machines cannot notice that. They don't get their attention distracted, focused towards things that don't work right. And that's what our brains are really good at. Right? So on one side, we get distracted by irrelevant things, and maybe some things we shouldn't be distracted with. But then on the other side, we also get attracted our attention to the problems, to the things that don't work. And we are able, therefore, to solve them. Machines can't do that. When things are going wrong, they just keep doing it wrongly. Okay. Second difference, very important difference, is concepts. So consider a concept of a chair, which is necessary in order to recognize, detect the chair. So how would you train a deep learning network? Everybody knows here, I think, how to do that. And for that, you need lots of examples of chairs. 8 examples of chairs is not enough. You need more, like 1,000 or 1,000,000. And then you could have an AI that can do chairs. And you can say, look, I have an AI that recognizes chair and distinguishes that from cars or whatever, or windows or flowers, animals, and so on. But there's still a problem. There's still a big difference between how humans do chairs and how machines do chairs. Check this chair. This is a very unusual chair. And if you give typical examples of chairs, then a machine will not be able to recognize this chair. Neither will be able to recognize this one or that one, or this one here, right? And I have even more weird chairs that AI algorithms will have hard times with, and we humans can do, because we have actually proper concepts. Right? Look at this chair, look at that chair, and this one, right? And why is that? That's because our concept of a chair is not only just about features that the chair has, it's about what it does to our body, how it helps us relax and sit down. Right? So the concept is about sitting. So this is also a chair. We can also see a chair here, and the AI algorithm cannot see a chair here. And we can also see different types of chairs even here, right? And here's even more weird chairs that the machines would have a really hard time distinguishing, right? So we have concepts that are much more powerful, and we don't use them just to recognize things. We also use them in many other very useful things. So check out this kit. Now let's talk about recognizing cars rather than chairs. This kid could see a car for the first time in his life and play with this toy for half an hour and sit and push around, turn the steering wheel, and so on. The kid acquires the concept of a car. Now after that, you draw something like this to a kid, and you ask what is it. The kid may know at first agree that this is a car, but then you say, look, it's a car, and the kid then would recognize, so, oh yeah, it looks like a car. Now comes the power of a concept of a car. When you draw this, and if a kid has ever played with a train, it will realize that it will recognize here a train. If this drawing before was a car, this drawing here can be a train, no problem. Only our brains can do such a shift in concepts. The machines cannot even get close to it. And we can do even more. Check this out. I go back to this one and I tell you, look, that's not a car anymore. It was a car, but now I shift your concept. I shift your perception. I change your mind. This is now a table with 2 chairs. Boom, no problem. I just completely converted your perception with a couple of words. And now, if this is a table with 2 chairs, what is that? Right? Do you see a classroom here? Do you see a restaurant here? Sure you do. You see how flexible your concepts are. Machines can do nothing like this. And all that done by seeing just a couple of examples of cars and a couple of examples of tables with chairs, not millions of examples. Right? And it is concepts that make us so intelligent. And we have some very important concepts in our lives, like the concept of self that has lots of subcomponents, lots of sub-concepts, like our name, our looks, our goals, what we like, don't like, friends, and so on. This is one very important, big, elaborate concept we have. We have also a concept of time is very important. We structure our memories along the time, understanding of the world's events. It's very much organized along the time. Then another importantly is related to profession, depending on whichever profession you do. There's lots of rich conceptual structure over there. Right? That's how we get intelligent, through concepts. And self-awareness is a concept of something that we call self. Right? So, for example, somewhere in the history, for the first time happened that someone said, "Holy smoke! I'm standing here." That someone has noticed the relationship between the space, relationship between an organism, that's me, and the relationship and the posture of a body standing. And this relationship, three concepts playing around, making one representation, one dynamic. It's an insight about the self-awareness, and that's something that happened for the first time somewhere in the history. Because what scientists, brain scientists, very often like to point out is that self-awareness is one of the key intelligence and consciousness advantages of humans, and other animals have much less of that. Right? It's all about concepts at the end. Right? The next difference, context. We humans love context. Machines don't like context. Our machines just don't care much about context. And to prove that, for the purpose of this talk, I made a test. I took Cortana and asked her, what is the capital of Germany? And Cortana correctly said Berlin. And then I said, and of France? And what do you think Cortana answered? Did she say Paris? Which would be a proper understanding of context? No, she didn't. She said, I pulled some images of France for you. Cortana did not understand a basic concept that come totally naturally to us humans. And of course, Microsoft engineers could build something in a machine to understand in this particular case that I'm still talking about a capital city, but this is not natural to the way how our technology works. For our humans, context is natural. For machines, it's not. And when doing that, I noticed something quite interesting about these assistants, and that's about their logos. This is the logo of Siri. This is the logo of Alexa. This is the logo of Cortana. You see a pattern here? Now, the logo of Google Assistant, does anyone remember? Here we go, right? You see a pattern here? So where do these circuits come from? I asked myself, why circuits? Where do they come from? And then I remember something from a history of science fiction of artificial intelligence. And it's this guy here, right? Which is a computer in Odyssey 2000 something. Right? And then we got also this circuit here that we talked about already. Right? So it's all about circuits for some reason. Okay, anyway, for machines, random stuff is perfectly fine. Machines like random. Even if you, deep learning likes random, and if you, even for learning, you probably all know that your samples need to be randomized to get good training in deep learning. And that brings us to the fourth difference, which is learning. How we learn. And to point out this difference, I made a little video here. I made a collection of random images, and I made a video that makes you experience what is it like to be a deep learning network in a learning experience. So this movie here that I will just start in a moment is basically has a random sequence of random images. I literally Googled random images, put them in a sequence, and then mark them. I label them. Living, not living, living, not living, living, not living. And now I play this movie for you so you can enjoy, you can feel what is it like to be a deep learning network. All right. So did you like it? Did you enjoy it? Probably not. That's not something suitable for a human. What we humans need is a story. Story is a context. So one event happened and the next event happened related to the previous event, happened to the next event, and so on. It has to have a story. It has to have a continuum of events. So to show you that, I now show you exactly the same images that you have seen now. Exactly the same random sequence, but I add a story to it. Right? So it starts like that. this. Once upon a time lived a dwarf named Pepito. Pepito had a dog, Barfi. One day they hit the road and tossed a coin to decide where to go, and decided to reach Antarctica. They didn't trust airplanes, so they traveled through Africa, from Europe, obviously, by train. When they reached South Africa, they waited for a boat. While waiting, they went for a dive, where they met Horatius, who took them to Antarctica on his back, and success at the end. Right? So it's the same random sequence of images, but if you put them in a story, then now they make sense. Now you remember them. Now if you meet me 2 years later and we discuss the story, you will remember the story. You will remember part of the story. The first thing that's good for deep learning network, it was totally confusing for us. And also it's important to know that the stories do not evolve for us only in time, they also evolve in space. So this here is one famous painting from a Russian painter called Ilya Repin. And the name of the painting is They Did Not Expect Him. And it's a static painting, and yet it tells a story. And to discover the story in the painting, what you need to do, you need to watch it for a little while. You look at one part of the painting, you detect what is there going on, you get like one message, then you move to another part of the painting, you look what's happening there, and then you go around and you build your story. And only at the end, you have an understanding of the painting, right? And in neuroscience, we can also have machines to track where people are looking, so we can see how people are thinking and building their understanding of the story. And that's pretty much what you get when people are looking at the story. So what happens is that you look at one person and then you look where this painted person is looking. Then you also are interested. Where is this woman looking to? And then you see this guy here. Then you are interested, where is this guy looking? And you go back and forth. And that's how we build this image. Right? So it's again a story, it's again context, just in space. Okay. Difference number 5, creating new concepts on the fly. It's not that we have lots of concepts, but we can create new ones on the fly quickly. So I'll create for you a crazy concept that I'm sure didn't have before this. And this is the concept of a banana riding on a bicycle. And to help develop this context, I first can give you a static image where you can again spend a little bit of time and looking around and you understand the relationship and you build your concept. But then I'll give you even a stronger story. I'll tell you about a poor village in Africa in which people work hard to survive, and they have to go long distances to get food, to get what they need to make sales. And one of the things they do, they go to the local market and sell bananas. And they have a bicycle as only transportation tool. And the one who is riding on a bicycle in this process is not humans, it's the bananas who need to be taken to the market, right? So now I created for you a concept, for you, a wonderful concept that's probably you'll never need it again. Right? Difference number 6. Working memory. Working memory is something amazing we have. And to show it to you what working memory is, I'll have a little experiment. It looks like experiments we actually do in lab in neuroscience, right? So what you will have now in the task, you will have one image appearing, that will disappear, then the next image, and you have to detect differences, right? So, ready? What has changed? The question is, what has changed? And most of the people would successfully detect a change in this task, and that red and yellow have exchanged places, and those who are really attentive would also notice that the nuance of a red color has changed as well. Right? And this is quite easy to do well, because this task is within the limits of our working memory. Our working memory is somehow limited to about 4 things. If I put 5 or 6 colors, you would have really hard time detecting. Only by chance you could get it right. Now that's really amazing. How is that possible? How does this make sense that our memory is only 4 items? We are so intelligent and we have a memory of only 4 items. Compare that to machines. Machines can memorize every single pixel. We have a machine that can memorize millions of pixels in an instant. We call it a camera. This machine is called a camera, and this machine is looking at me right now and sending these pixels to you. And why are we so have this wonderful brain with 80 billion neurons and we can remember only 4 things? What the heck is going on? How is that fair? And how is that possible? And to explain that, let's get the second experiment, like very similar one, almost the same one. Also with 4 elements. I give you 4 elements, right? Ready? Was this one in the first group of 4 or not? And now, if you are not a Chinese writer of Chinese characters, right? You can't tell. You have no idea. We are still back to 4, but you can't tell. Why? Not because these characters are more complex. It's only because they're more complex for us, for Europeans who are not trained in Chinese characters. We do not have concept for each individual character. And Chinese people have. And if there's Chinese people in the audience, it was obvious for them that this character was present. And they even noticed very clearly that I turned it upside down, right? It's no problem for them. For us, it's hard. So the answer to the question of working memory, why do we have this limited working memory and why is it only 4, is that because we work with 4 concepts. We can have 4 concepts at a time, working together, fighting, collaborating, finding out solution to a problem, negotiating among themselves how to navigate a situation. That's actually the core of our intelligence, is these 4 concepts at every moment in time, working out and solving problems and coming with new creative ideas to solve problems. Some things machines cannot even be close today of doing. And finally, difference number 7, that's the last one. We do not have only these wonderful concepts, and we are not only working through context and all these things, but we have long-term goals and we have multiple ones. And in addition, we have entertainment. Our AI does, not AI, biological intelligence, so BI. So I'll go through this really quickly in the interest of time. So we can have really long-term plans like graduating from school, building a home one day, or retirement, right? And we have to do all crazy things for entertainment, like these people here. There's a sport discipline that you may never heard of. It's called extreme ironic. And these people won one of the competitions on extreme ironic, right? So crazy stuff just for fun, right? And finally, here's the conclusions. So what are the conclusions? The brain and machines work fundamentally different ways. Only we humans and we biological machines use concepts. Animals as well use concepts, just like humans, and context and stories. Machines are not anywhere close to reaching human intelligence because they don't have concepts, context, and stories, and don't do vigilance errors. So for the foreseeable future, humans will have jobs. Machines will not take over. And here's my final video. I want to show you. I started with the problem of robots not being able to do dishes, and we needing robots to do dishes. And and the point is that animal brains are, of course, much more similar to human brains and work in a similar way, not like machines. And animals can do dishes. And here's a proof that animals can do dishes. It's nothing that robots could do. Look at this dexterity and this capability of manipulating all these objects. Okay, good. So thank you very much for your attention.